Today we're going to talk about recursion, which is going to lead to talking about the call stack. We're going to walk through a few examples, and then we're going to talk about recursion as it appeals to both arrays and strings, and also just some kind of best practices regarding recursion. So let's get started. The short, succinct, punchy definition for recursion people always use is recursion is when a function calls itself. And it sounds really simple, but then when you think about it, it actually could cause kind of a headache because it's sometimes not very clear what it means when you say a function calls itself. Like, what does that actually mean? A lot of times, especially for the things we're going to look at today, you might even ask yourself, well, why do it with recursion? I could do it with a for loop. And you're completely right. Most of the things that we want to do with recursion for today, we are able to do with a loop, like a while loop or a for loop. However, as we get more advanced and you get into more complex recursion-based topics, you actually very soon realize that there are some problems that we can only solve with recursion. So in the real world, the reason why recursion is so powerful is because it really allows you to break down the problems into smaller and smaller pieces, and it lets you solve kind of a very minutiae part of the problem in a very scalable way. And I know these are just words I'm saying right now, but hopefully very soon you'll kind of see how that applies to problem solving in the real world. And lastly is just because it's once again it's something that can solve a certain class of problems that you can't solve any other way. So just some buzzwords to throw out there at you. Okay, so before we talk about recursion, let's talk about the call stack. The call stack is a fundamentally core concept to understanding programming because the call stack really it determines the order in which our code actually executes. JavaScript is a single-threaded language, which means that you can only run one function at a time. And indeed, we've kind of seen that throughout this entire curriculum, right? When we write code from top down, we might jump around depending on what function is being called, but the key thing here to remember is that we never move on to the next thing until we finish our current thing. As in, if I have on line 1, I write console log 1, and on the next line, I wrote console log 2, I would never run console log 2 before I finish running console log 1. And so that's what single-threaded means. It means there's a very clear order in which the code needs to run, and the code will only move on to the next line once it finishes with its current line. So having said that, the call stack then becomes a structure that JavaScript uses to figure out which function should be running at which point in time. The best way that I've heard to describe a call stack is it's like the stack of plates at a buffet line, right? And so what makes that stack unique? There are two parts. The first one is if I have an empty plate and I want to put it on the stack, I don't move all the plates and put it on the bottom of the stack. Instead, I just put the plate on the very top of the stack. And so this means whenever I need to add something to the stack, the plate always goes on top of the existing stack. On the other hand, if I want to take a plate off the stack, I'm once again not going to move all the plates off the stack to grab the one on the bottom. I'm just going to take the plate that's at the very top. And so this means whenever I'm trying to take something off the call stack, I always take what's on top of the call stack at the current point in time. And so here, if I apply this to programming now, on line 5, I have a function called first, which just console logs that I am first. I have a function that console logs that I am second. Here, the point is to say that on lines 5 through 11, I basically created two functions. I haven't ran anything yet. On line 13, I actually run the first function. And when I do that, my call stack says, great, David, you're going to execute the first function. And so I do. After I execute the first function, I console log out I am first. And then when I'm done with a piece of code, when I'm running a piece of code, I put it on the call stack when I'm running it. And when I'm done with it, I take it off the call stack. Pretty straightforward. So here I ran and finished the first function. And then I add the next line of code, which is the second function. I run that function too. It prints out I am second. And I take the second off the call stack, and now I'm done. Okay, so a very, very basic kind of, hopefully a little bit graphical understanding of how a call stack looks. Now, if I was to write a function that's a bit more complex, for example, a function that takes in a number and counts down from that number all the way down to 1, well, one easy way for me to do it could be with a for loop. Here, I have a function called countdown. I take in a num, and all I do is I run a for loop that starts at I equals num, and then while I is greater than or equal to 1, I subtract 1 from num. And so when I run countdown of 5, what happens then is it's going to feed in 5 as num. The for loop's going to run 5 times, and each time I'm going to print out a number until I get to the very end. But if we take this now and we combine these two ideas of, hey, how does or if we combine these two ideas of how a call stack works in conjunction with how a loop works, well, actually it becomes a little bit more, it actually becomes a little bit more nuanced. Here, I still have my first function, but notice here when I run my first function, on line 3 there, on line 2, I console log out I am first, and then on line 3, I actually execute another function. And then on line 4, I console log out another line, which is called first is finished. If I look at my call stack, and then I define my second function as just logging out a simple message. Now, when I execute my first function on line 11 there, my first function goes on my call stack. So far, so good, right? I'm executing the line of code that's currently being processed. But then I print out on line 2, I am first, and then I hit line 3. And line 3 says, well, in order to finish running this first function, you actually need to also run this other function called second. So then I'm in a position now where I have to actually run the second function. And now my second function is kind of like going back to the plate analogy, the second function is being stacked on top of my first function. And notice how like here, I'm not removing the first function off my call stack because I haven't completed it yet. Instead, I put the second function on top of the first function because in order to finish the first function, I need to finish the second function. Is that making sense to folks? Right? Running the second function is a requisite for finishing the first function. And so therefore, when I put the second function on my call stack, if I go back to one of my earlier ideas, which is, well, when I have a call stack, what do I do next? I do whatever is on the top of the call stack. Here, my next job is to actually finish running the second function. So when I do, I console log out I am second, and then I'm done with the second function. So then I can take it off my call stack and I resume where I had left off with the first function. And here I console log out first is finished and I'm done. Okay, so once again, this is just to reiterate the idea that here, because in the first function on line 3 there, I'm actually calling the second function as well. It's very important to me because in order for me to run the second function, I need to run the first function. Cool. So let's take a look at our old countdown solution now, and let's just refactor it out a little bit more differently. So before I have my for loop, which goes through the number and prints it out. Nothing wrong with that. But let's think about another way to approach this problem. Here on line 4, I have a function called countdown, which just takes in a num and logs out the num. Well, another way for me to count down from 5 all the way to 1 is just to almost very dumbly say, well, let's just print down countdown 5, 4, 3, 2, 1. But that seems a little bit very manual, right? Sorry, do you guys hear a lot of background noise coming in on my side? Is it bothering you guys, or is it fine? Okay, cool. Yeah, let me know if it gets too loud. Sorry, there's people in the background, and I can ask them to tone down a little bit if we need to. In any case, every time we call countdown, notice how on the previous page, every time we call countdown, we subtracted 1 from the previous number. So rather than having to manually write out countdown 5, countdown 4, countdown 3, and so on and so forth, why not just have the function call itself? And each time we call it, we subtract 1 from that number. And so here on line 7, I have a function called countdown. I pass in a num. And on line 8, I console log out the num. And then when I'm done with that, I actually call countdown again, except now I'm passing in num minus 1. And so when I do countdown 5, my call stack actually looks something like this. The first time I run it, I count down, I am console logging, I am countdown, countdown 5. Well, when I do that, I print out 5. And then the next line here is saying, okay, well, in order to finish this kind of line of code, you need to finish countdown 4. But because I can't finish countdown 5 until I finish running countdown 4, I now have to run countdown 4. Well, countdown 4 is going to make me print out 4, but that says you need to finish countdown 3. So I print out 3, but that says I need to finish countdown 2, and so on and so forth. Except we kind of reach this condition where I never really stop, right? I just keep calling this countdown function over and over and over again. You can kind of see how my call stack is going to inevitably get out of control because it's never going to stop. And so this is a very common issue when people use recursion is they actually have this really cool pattern where they start calling this function over and over again, but they don't tell the function when to stop. And so in most modern computers, when this happens, the computer won't break. It will just stop itself and say, hey, I think you made an error here. And so basically the takeaway here is the same as when we talk about the while loop, which is that whenever you write one of these functions, making it go is actually not that hard, but telling it when to stop is actually a lot harder. And so we need to figure that out. I mean, yeah. Can I stop for 1 second? I'm just going to move to another spot where it's a little quieter. Thank you. Yeah. Hey guys, can you hear me now? Is there still background noise? Okay, perfect. Sorry about that. Okay, sorry. So let's pick up where we left off here. So that function worked, but the only problem was we actually couldn't figure out when to stop. And so as with the while loop, whenever we write a recursive function, let's always specify when to stop. And so here, or rather not here, but in general in recursive functions, the point at which we stop is called a base case scenario. That's basically saying when do we stop calling ourselves. And so here on under countdown, on line 3, it says as num is less than 1, we console log out done. Else, we console log out the number, and then we call countdown of num minus 1. And so now when we do countdown of 3, the pattern that we're going to see is something like this. We're going to do countdown 3. It's going to print out 3. Then we're going to do countdown 2. It's going to print out 2. And realize I'm kind of skipping over a little bit, but each time we run countdown 3, we go into our if loop and we say is num less than 1. And so 3 is not less than 1, so we go to our else statement. And when we call countdown 2, is 2 less than 1? No, it's not, so we go to our else statement. Which to make us call countdown 1, is 1 less than 1? No, it's not. So we go to our else statement, we console log out 1, and then finally we go countdown 0. Well, 0 is less than 1, so then we console log out done. And at that point, when we console log out done, we skip the else statement because we are already in our if statement. And that means we're done with our countdown 0. So we take it off our call stack. So then we pick it up where we left off on the countdown 1, which was also just, that was the last thing we had to run. So we're done with that. And it takes to finish countdown 2, then countdown 3, and then our function ends and we're finished running our countdown function. Did that make sense to everyone? Yep, there's no for loop. You mean decrementing? On line 9 there, notice how each time we call countdown, we feed in num minus 1. So every time we call countdown, the number is getting smaller by 1. On line 9? Cool. Okay, is everyone good? Yeah, so it's not a loop. There's not a loop because a loop basically says, hey, I'm controlling what's going on each iteration, right? Here we're just saying every time I'm just going to give you a smaller number and you do what you do. And so that's why when that's why the countdown 3 goes to countdown 2, countdown 1, right? When I call countdown 3, num is equal to 3, right? When I get down to line 9, it's saying, hey, call countdown of 3 minus 1, so countdown 2. So the next iteration of the countdown function, or sorry, the next time I run the countdown function, I'm feeding in num as 2. But it's a completely different run of countdown 2 than countdown 3. Like countdown 3 triggered countdown 2, but they're different runnings of the same function. Does that make sense? Yep. 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 Okay, so walk me through this. So let's say I run countdown 3, right? That takes me to line 1, and now num is equal to 3, right? Yep. 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 Yeah, yeah. I mean, yeah, yeah. So countdown is a function, right? And whenever we have a function followed by an open and closed parentheses, that just means run the function. Like there's actually no way for us to write that without running the function. Okay, so the way the way to think about this, and I think I kind of see where your confusion is here. The way to think about this is that it's like let's say so I'm not sure if yesterday or before you guys had heard the analogy of a function is kind of like a recipe, right? Like I can run it over and over and over again. So think about it this way: if on this one is this countdown of three, let's say it's like a recipe and saying, hey, bake this cake with 3 chocolate chips, right? And the very last step of that recipe says bake another cake with two chocolate chips, right? We're not trying to shove 2 chocolate chips into the existing cake. We're making a brand new cake, right? We're executing another implementation of that recipe. Yep. Yes. Yeah. No. No. Yeah. No. Yeah. And don't get too hung up on the terminology here. Like, does the flow of the code make sense to you? Okay. Great. Well, recursion by definition just means when a function calls itself. So if a function doesn't call itself, then it's not a recursive function, right? Yeah. No, no. I mean, it's like saying like like can I have a football team without a quarterback? It's like, well, you could, but it's not really a football team anymore, right? Or maybe that's not the best example, but you kind of get the idea, right? Like we can have a like recursion is more like a technique. It's like a description for something. And it's like, can I have a red ball if it's not red? And it's like, well, you just have a ball then, right? Like a recursive function without a recursion, without a self call is just a function, which is totally fine, right? But it's like recursion by definition means something, and so we need to kind of follow that if we want to use that terminology. Yep. Cool. Yeah, and you're clear on line 9, like that's where we run the countdown function again, right? Yep. Yeah, no problem. This is now a loop. No. Yep. Yep. Sure. Yeah. So to take away countdown, one is we need to find a base case, i.e., when we need to stop. In this case, this was in our if statement from the last example. And then secondly is because we're calling a function over and over and over again, at some point we need to get to a point in which we will eventually reach our base case, right? Point number two is just a fancy way of saying, look, at some point we need to reach a condition in which we are able to stop. Recursion becomes more complicated when the function has to return a value. Remember, console log just prints out to the screen. It doesn't actually move any values back and forth. Returning is actually us passing a value back and forth. Um, and so, yeah, so these are just some best practices. Define base case first, and then have a simple input and make sure that it works with smaller values before you go to the bigger values. So let's just take another look at another example. It's probably a lot easier to illustrate these concepts. Let's say I want to make a function called a factorial. What a factorial in this function, also in math, what it does is it takes a number and returns the factorial of that number. The factorial number is just the product, so that number multiplied by every number between itself and 1. So the only kind of edge case is the factorial 0 is 1, but the factorial 1 is also 1. The factorial 2 is 2 times 1, so 2. The factorial 3 is 3 times 2 times 1, so 6, and so on and so forth. So let's write a function in which I'll give it a number, and it'll give me the factorial of that number. Well, if we think about it, the base case basically says, when do we not need to figure out when do we not need to figure out whether or not when do we not need to do more multiplication? Well, we know that when the factorial, just go back to the previous page for 1 second here, when the factorial is 0 or the number is 1, the value is just 1. There's nothing we can do, right? It's kind of like a given. So in that case, if num is 0 or num is 1, well, let's just return a 1. That's our base case, right? Right now, this function is now recursive. We don't call ourselves anywhere. And if I do factorial 0 or factorial 1, we get back 1 and 1. Okay, very straightforward. Nothing. Hopefully, that's confusing. But now that we've set our quote-unquote base case, and once again, the base case is just saying if this is true, don't call ourselves, and we already finished that. Well, now let's figure out something else. Well, if we go back and look at the function again, the factorial of 2 is actually equal to 2 multiplied by the factorial of 1 less than 2, so factorial 1. And the factorial, and just jump down to line 12 here, the factorial of 5 is 5 times 4 times 3 times 2 times 1, but 4 times 3 times 2 times 1 is just the factorial of 4. And so factorial of 5 is just 5 multiplied by the factorial of 4. And in fact, any number is just equal to that number multiplied by the factorial of 1 less than it. And so here, if we want to think about this a little bit more in depth now, if num is 0 or 1, we just return a 1 because that's what our value is. But if the value is greater than 1, well, the easiest way for us to do a bigger number is actually just to do that number multiplied by, well, in this case we haven't done it yet, but the easiest way to do it is just to do that number multiplied by the factorial of 1 less than it. So here, on line 9, we're going to use the console log just for now, and we'll change this later on. But here, if we do, what's factorial of, if I do factorial of 2, what's factorial of 2 minus 1? Well, that's just factorial of 1, which is going to give me 1, right? So I'm not quite there yet, but I'm getting close to it. Because here on line 9, I'm actually calling myself. And just so we're clear, on line 4, we're returning something. So we hit line 4, our function ends. And so therefore, we will only hit line 9 if the if statement is not being triggered. Okay, so this is a lot of setup, and actually I might go through a little bit fast just because I want to get to the end of this slide, or sorry, the end of this example, which I think illustrates the concept very well. So here we're saying, once again, if the factorial of a number is just that number multiplied by the factorial of itself minus 1, well, on line 8, we basically have that math, right? Num multiplied by factorial of num minus 1. And indeed, if we just do something like, if we use a return value instead of a console log, we're actually going to get the right answer here. And because here on line 12, if I do factorial of 2, well, if I step through this function, on line 1, we say num is 2. Great. On line 3, we ask, is num 0 or 1? Nope. Great. So look at line 8. Line 8 says, result is equal to num, which is 2, multiplied by the factorial of num minus 1. So what's 2 minus 1? It's just 1. Okay, great. So before we move on to line 8, we have to figure out what factorial 1 is. That means on line 8, we're actually calling the factorial function again. And so in another separate run of factorial function, we're passing in num. We're passing in 1 for num. And so on line 3, we say if num is equal to 1, then we return 1, and we're done. So then we go back to where we were before, and now line 8 becomes let result equals num, which is 2, multiplied by the factorial of 1, which we determined was 1, and so therefore we get 2. Is that making sense to folks? 3? Yep. Yeah, no, it's a great question, and we have the slides right here for it, right? So let's walk through a factorial of 5, right? Like a, not a huge number, but a bigger number, right? Well, the first time we run factorial of 5, we go to our if clause. Is num 0 or 1? Nope, it's 5. Great, let's go to line 7. And line 7 says, great, result is equal to num, which is 5, multiplied by a factorial of 5 minus 1, which is factorial of 4. Well, that means I need to call factorial of 4 to figure out what factorial of 4 is, right? Well, factorial of 4 says, okay, great, let's run through this function again. It's not 0 or 1. Well, factorial of 4 is 4 multiplied by factorial of 3. So now we figure out factorial of 3 is, right? And look at my call stack, right? At each juncture, I'm just doing factorial 1 minus 1. And finally, I get to factorial 1. What's factorial 1? It's just 1. Great. So I go back to where I on the previous iteration, I now replace factorial 1 with just 1. And now I know what factorial 2 is, 2. And so then I go back to where I had called factorial 2 and replace that with 2. So now what's factorial 3? Factorial 3 is now 6. Factorial 3, I replace that with 6. Factorial 4 becomes 4 times 6, so 24. And then factorial 5 becomes 5 times 24, which is 120. So this factorial function is going to call itself over and over and over again. But the goal here really is to just make sure that at the end of the day, we get to our end state, which is where num is 0 or 1. Everyone clear? Sure. Okay, so here if I want to call factorial 5, um, do you understand how we get to line 7? Yeah. So line 7 says, okay, great. You need to tell me, before we move on to line 8, you need to tell me what num multiplied by factorial of num minus 1 is. So that's why on my right-hand side of my call stack, I'm trying to figure out the return value for what 5 multiplied by factorial 4 is. Good so far? So in order to figure out what factorial 4 is, well, I need to run my factorial 4 function. And on that iteration of the function, it's going to take me to line 7 again. And that says, hey, you need to figure out the value of factorial 4 is just 4 multiplied by the factorial 3. Oh, sorry, guys. Can you guys hear me on Zoom still? Okay, I guess that wasn't a real thing then. Okay. And so I just kind of keep going on this sequence again. And finally, I get to a point that says, okay, factorial 2 is equal to 2 multiplied by factorial 1. Well, what's factorial 1? It's just 1, right? Good? You good? Are you good? Okay, great. So now, if we know factorial 1 is 1, and factorial 2 is just 2 multiplied by factorial 1, that just means factorial 2 is just 2 times 1, right? Which is 2. Great. And well, we needed to figure out what factorial 2 was because we needed to figure out factorial 3. Because 3 multiplied by factorial 2, or factorial 3 is equal to 3 multiplied by factorial 2. And what's 3 times factorial 2? It's just 6. Yeah, because that's what the value is once we do the math and figure it out, right? And it's like basically this, like we're just building. These are like the building blocks for our to figure out what factorial 5 is, right? And once we know what factorial 3 is, well, the reason why we need to know what factorial 3 was because we were trying to figure out factorial 4. We know that factorial 4 is 4 multiplied by factorial 3. And so if we know factorial 3 is 6, then factorial 4 is just 4 times 6, which gives us 24. And then we feed that back into 5 multiplied by factorial 4. So 5 times 24 is 120. Cool. Does that make sense to folks? Yeah. Sure. Okay. So let's see. Yeah. So for example, so like I said, like for today, we just want you to use it and get familiar with it, and we're very aware that all the things you do today, you could do with a for loop. For the next class, so we're doing 2 sections on recursion. For the next class, you're going to encounter problems that you're not going to be able to do without recursion, right? And usually those have to do with problems that have to do with unknown quantities. So for example, let's say we all know that we can put arrays in other arrays, right? And we can put arrays in those arrays too. So we can have like a very complex nested arrays, right? So if I was to say, well, can you write me a function that goes through every single nested array in this array? Well, you can't do that without recursion because no matter how many for loops you write, if you say, hey, I assume I'm gonna write a for loop that goes in 100 levels deep into this array, well, what if my array is nested 101 levels deep, right? So you don't know when to stop. And so because of that, recursion actually becomes a very powerful way of solving the problem. So like it's hard to explain without giving you a real example, but then if I give you a real example, it will lead into the next class. So it's a little bit of a chicken or the egg problem right now. But for us, just kind of bear in mind that there are problems that you can only do with recursion. But the ones for today, you can do it multiple ways. You can do it with a loop or with recursion. And so we just want you to get familiar with it first. Is that good for now? Yep. Okay, so recursion, you can use it any data type in JavaScript. A lot of times it'll ask you to go through arrays or strings as well. And so things like finding the sum of numbers in an array. If the array has just one number, it's length 1, it's easy to find. But otherwise, if you just think about this idea of like, well, if I had to add up all the numbers in an array, well, basically I just go through this array until I get to the end of the array, right? Once again, I know you could do that with a for loop very easily, and you're probably more comfortable doing it with a for loop. but for today, really challenge yourself to use recursion. It's kind of the purpose of today's lesson, if you will. Okay. Other recursive hints. Always have a base case, because that means you need to know when to stop. Test with an easy case first before you go on a harder cases. And the last thing is just don't confuse what return with console logs is, right? Return means passing a value back. And so whenever you're writing a recursive function that needs to pass values back to each other, always use return. On the other hand, if you're just printing out values, console logs is probably going to be fine. Yep. Okay, so that's pretty much it for the lecture for today. Like I said, and I can't stress this enough, it's going to be easy for you to, maybe even enticing for you to take a shortcut and just say, oh, let me just